Welcome back. We are going to continue the second example of repeated eigenvalue for 2 by 2 homogeneous system. Okay, for example, to solve the y prime equal to 1, 9, negative 1, negative 5, y, given the initial condition when t is 0, y is equal to 1, negative 1. Okay, as we have learned in previous example, we assume the solution y is equal to eigenvector v exponent lambda t. Then we have the system actually y prime equal to a y. So y will be substituted by v exponent lambda t. So y prime, so you need to differentiate y, you get lambda v exponent lambda t, and then we cancel the exponent lambda t broken side. Here you get a v minus lambda v equal to 0. Factor out the here v. Since a is a matrix, to do the matrix operation, lambda is a constant value must multiply by an identity matrix which is same dimension with the a. And since k vector v cannot be 0, if 0 then the y has no solution. Hence k can have one and only one solution, which is determinant of a minus lambda I equal to 0. Solving determinant of a minus lambda I equal to 0, you can obtain the value of eigenvalue. Plug in the eigenvalue, you can find the solution for the eigenvectors. So in this case, our a is actually 1, I, negative 1, negative 5, a minus lambda I will make the changes at the diagonal value here. So you got 1 minus lambda, negative 5 minus lambda. So this is a minus lambda I. Okay, this is a b that we are going to find. We let it equal to element x and y equal to a 0 vector. Once we obtain the lambda I, then we can find the eigenvector. Okay, and then plug in back to our assumption, then we can solve for the homogeneous system. Plug in back the eigenvalue lambda and we can find the solution for the homogeneous system. The first step, we let the determinant of a minus lambda I equal to 0. So determinant of a minus lambda I equal to 0. Now, to find the determinants, we have the main product. Diagonal product of the main diagonal 1 minus lambda times negative 5 minus lambda, so minus 2. Negative 9, so become plus 9. Expand and simplify, we get again here we have the same eigenvalue, which is lambda 1 equal to lambda 2 equal to negative 2. So second step finds the a minus lambda I v1 equal to 0. But plug in the lambda actually equal to negative 2. So a minus negative 2, we have a plus 2. So only change at the main diagonal. Obtain here, and we notice actually these two rows are equivalent, or means you take let's say row 1 divide by negative 3. Okay. This negative 1, this is negative 3, xy equal to 0 vector. So these two equations with two unknowns is actually reduced to the same equation. Then if I multiply here, multiply by negative 1s, then I get actually if you multiply by negative 1, so x plus 3y equal to 0. So we let x equal to negative 3y. Then y equal to s, hence x will be equal to negative 3x. So you have xy. So y is 1s, x negative 3s. By letting the s equal to 1, you get the v1 is actually negative 3 and 1. This is V1. Y1 is the V1 multiplied with exponent lambda. Lambda is negative 2. Okay. To find the V2 as in the previous case video, we have mentioned that you let A minus lambda I V2 equal to V1. V1 then obtain 3 negative 1. So the left hand side part will be same in the step 2. Because your lambda is actually lambda is negative 2, so it's not 2. So this case, so minus is negative 2. So you got plus 2. Plus 2. So 3, negative 3. Okay, as in the step 2, we said these two rows are actually, you can reduce to the same equation. If you take, let's say, lambda 1, you divide by negative 3. So you have negative 1, this is negative 3. Then this is xy. 3 divided by negative 3, this is equal to negative 1. So there's no changes on your row 2. So you can see that both equations actually you reduce to the same equation. And then equation 2, to eliminate the negative, we can multiply both hand side by negative. That's why you have with row 3 later on we find with negative and with negative. So you get actually become 1, 3. Then you have xy equal to 1. Because these two rows actually the same. We will find this one by negative, so positive, positive, positive. So x plus 3y equal to positive 1. Compared to the step 2, this will be x plus 3y equal to 0. So the difference here. Because in step 3 is actually you solve a minus lambda I v2 equal to v1. In step 2 is this is equal to v3 0. That's why the difference is only at this part. Okay, and for repeated eigenvalue, if in step 2 just now you let y equal to s. Okay, and then here you must have the same assumption. Y equal to s. So this one I put is y equal to s. Because the typed and what I written is different. Okay, if I let's say y equal to s just now, so y equal to s. Then I have x plus 3s equal to 1. So my x is actually 1 minus 3s. Okay. So my xy, x I have 1 plus negative 3s. Y is 0 constant 1s. So the new constant vector will be my v2. Okay, a vector dependent on s will be my v1. The answer, the typed and the written is different because my typed here, the newly in the red color, I let y equal to s. So x is negative 3s. Okay, if you let x equal to s as in here. If I this one is opposite, I let y is negative s. So negative s, so x is positive. Okay, compared with this one, this is negative 3 and 1. If I multiply by negative 1, so this negative 3, this is positive 1. Doesn't matter. We may have a lot of variation of the eigenvector because we got infinite many solutions here. So, but make sure the same assumptions. In the red color, here I use y equal to s. So when the findings of v2 must be the same thing, y equal to s. Then only you can get back a vector that depends on s will equal back to your v1. If you change, then you will get back this pattern. So your solution, whether it's this form or this form, doesn't matter. Okay, once you plug in the initial condition, we have the same solution. So now we follow the type 1, the V2 is 1, 0. Okay, so the Y2 will be V1 T exponent, okay, it's 1 T or negative 2T, okay, lambda is actually negative 2. Lambda is negative 2. So this one is negative 2T, negative 2T. So V1 you may have another variation just now, maybe it is negative 3 and positive 1. Both are same, different variation only. So if V1 T exponent, the lambda because it's negative 2. So T exponent negative 2T plus V2 exponent negative 2T. Hence the general solution we have is A Y1 plus B Y2, where the Y1 is actually B1 exponent lambda T, V2 is actually V1 T exponent lambda T plus V2 exponent lambda T. So put in cell V1 the lambda value. So this is a general solution. So substitute the initial condition when T0, actually your Y1 equal to 1, Y2 equal to negative 1. Put it into, this one is actually, vector Y consists of Y1 and Y2. So Y1 is 1, Y2 is negative 1. Okay, and then when T0, the exponent 0 is actually 1. That's why this term is 1. Okay, T0, this term gone. So this one you get 1. So B times 1 and 0. And then you may use in your scientific calculator directly to solve for your A and B quickly. Okay. So to solve using a scientific calculator, is actually manually you have 3A plus B equal to 1. Negative A, don't have B, equal to negative 1. So we plug in the coefficient of a simultaneous equation into your scientific calculator. So this is simultaneous equation 2. So coefficient of your simultaneous equation, x is tally with A, y is tally with the B. So we got 3, 1, 1. Key in row by row. So negative 1, you don't have a B, so it's 0. Right hand side is negative 1. So x is actually the A, which is 1. Y is actually your B, which is negative 2. So you plug in back, plug in back the A and B. Plug in back the A and B here. This is a general solution. Plug in A is actually 1. B is actually negative 2. Okay, or you want to expand back the solutions, you neglect it here, this term and this term together. So 3 minus 2 times, so it's left 1 time exponent negative 2t for row 1. Second row negative 1 exponent negative 2t, okay, 0, so it's negative 1. Okay, or we want to expand some more into what is the y1. So y1 will be the first equation, first row, which is exponent negative 2t minus 6t exponent negative 2t. And then the y2 will be the second row, which is negative exponent negative 2t plus 2t exponent negative 2t. Okay, here I'm going to show you just now, if you have another variation of your V1, which is negative 3 and 1, negative 3 and 1, so means if in the general solution, this part is negative 3, this is 1. Okay, when you solve it, you should get the same solution. So we got another variation where my v1, by using scale y equal to s, my v1 is negative 3 and 1. And I got another variation, say my v1 mean the y2. I got another variation. This is negative 3. This is 1. This is t. This exponent negative 2t. Okay, plus. Let's see where v2 were the same. Okay, v2 same. Got the same v2. So 1, 0, exponent negative 2t. Okay. So mean my general solution. My v1, I got another variation. This is another variation, which is actually my v1 is in the negative 3, this is 1, exponent negative 2t, and then plus b, plus my v1, this is negative 3, this is 1, so t exponent negative 2t, plus 1, 0, exponent negative 2t. Okay. I'm going to show you, okay, you may have a lot of variation of your eigenvector. Okay, but when you plug in the initial condition, you have the same solution. So when you plug in, so when you substitute the initial condition, this part, you got this variation. So the blue, the black is a versions. V1 is 3, negative 1. The red color is a version V1 negative 3 and 1. So now I plug in the initial condition. So we have the same. This is 1, negative 1. So A, this is negative 3, this is 1. Exponent 0 is 1. This term is 0. Then we have 1, 0. Multiplied by 2. Because when t 0, this term gone. Only this term is 1. So 1, 0 times b. So solve this one using your scientific calculator. Then you got negative 3a plus b equal to 1. And then you have a equal to negative 1. Okay, we use our scientific calculator. Okay, now we got is actually negative 3. Okay, this is 1. Negative 3. 1, 1, right side negative 1, 0, and then a is 1. Now we get actually a is negative 1, b is negative 2. A negative 1. A negative 1, 3. 3 minus 2 is 1. So, okay. So, if you have this another variations, your V1 is negative 3 and 1. Okay, your A and B value is different. Okay. And you plug in into your general solution, the particular solution, the Y, okay, because your V1 is another version, this negative 3, this is 1, this is exponent negative 2t, okay, b is same negative 2, and then this is negative 3, this is 1, this is t exponent negative 2t, b2 is same, so 1, 0, exponent negative 2t. If we try to expand, we should get the same solution. Check. So, y. Collecting the x system. Negative 3 exponent negative 2t plus 1, so negative 2. Negative 3 minus 2 times negative 5. So negative 5, this is 1, okay, exponent negative 2t, so this is minus 2, negative 3, 1, t, exponent negative 2t. Okay, and then from here you expand, you should get back the same y1 and y2. Okay, y1 negative 5 exponent negative 2t add up with 6. So we have a exponent negative 2t. This is t1. y2 is exponent negative 2t minus 2t exponent negative 2t. This is my plus 6t exponent negative 2t. Okay, let me check where's the mistake. Suppose we should get back the same solution. This is negative 5. Okay, suppose we should get back the same solution. Let me check whether we got any mistake. Okay, from here, let's x plus 3y equal to 0. So x is negative 3y, and let y equal to s. Hence x is negative 3s. So y is 1s, x negative 3s. So my v1 is negative 3 and 1. Negative 3 and 1. So means I got another variation. My v1 is actually negative 3 and 1. And then I find from here, oh, I know what's a mistake, because here, okay, I know what's a mistake. Because my v1 is negative 3 and 1. Negative 3 and 1. So I cannot take from here. I must equal it to negative 3. This one is 3 negative 1, not negative 3 and 1. That's why you get the different solution. So means okay, I should have here. If I use this variation, okay, negative 3 and 1, then mine should be 3, 9, negative 1, negative 3, xy, this is equal to negative 3 and 1. Because this variation is v1 is 3 negative 1, where y is negative s. This is okay, y equal to positive s. And then okay, take row 1 divided by 3 and divide by negative 3, this is positive 1. Okay, but by negative 3. So negative 1, negative 3, this is get back positive 1. So I have the, and then this is negative 1. Then we have from here, if I take second equation here, multiply by a negative, so this positive x plus 3y equal to negative. From here I should have x, okay, plus 3y, because I multiply by a negative, so this is negative 1. Mistake here. And then okay, previously I let y equal to s. I let y equal to s here, hence, and also y equal to s. So x plus 3s equal to negative 1, hence the x is actually negative 1 minus 3x. So the v2 is here, negative 1, 0. So this is, if we use this is another version where y equal to, okay, this one is y equal to negative s. this is y equal to s. So the v2 you have negative 1, 0. Okay, and then we get back the v1 exactly negative 3 and 1. So my v2 difference, v2 is negative 1 and 0. v2 is here negative 1 and 0. Okay. So this is negative 1 and 0. It's negative 1 and 0. So negative 3a. So this negative b equal to 1. Okay. So the a and b value, a is equal to, so a equal to negative 1. So 3, okay. So b will be equal to positive 2. Okay, negative 3, this is negative 1 equal 1, and then 1, 0. A negative 1, B positive 2. B is positive 2. So this one B is positive 2, is positive 2. Oh, and my B1, this is negative 1, 0. So negative 3 exponent negative 2t plus 2 and negative 1, so minus, okay, minus 2, minus 5. Say minus 5 exponent negative 2t. And then say the second one, the second row, 3. So negative 5 exponent negative 2t minus 6t. Check, they got some mistake. So this one is negative 5 exponent negative 2t minus 6t exponent negative 2t. So this is correct. So for y2, 1 exponent negative 2t plus. That's correct. Oh, I know what's a mistake again. Okay, I know what is a mistake again. Okay, because here a is negative 1. Here. A negative 1, B positive 2. So for another variation in B1 is negative 3 and 1 because A we get A is negative 1. So A we got negative 1. So when it's negative, so you get back same thing. So first negative 3, so positive 3. So 2, I collect this term. So positive 3 exponent negative 2t term, 2 and with negative 1. So mean here I just left is 1. This one is actually 1. Positive 3, 2 times negative 1, 3 minus 2 we have 1. So this is negative 1. So this term correct, only the first term wrong just now, tally. So for another variation where the B1 is to get negative 3 and 1. So now I expand in here. So y1, 1 exponent negative 2t. this one, 1 exponent negative 2t minus 6t exponent negative 2t. So now both quotients are tally. Okay, for y2 second row, negative exponent negative 2t plus 2t exponent negative 2t. So negative. Okay, so now both versions are tally. Because we do two versions on the same paper, that's why a bit messy. Yeah? So I repeat it one more time. This is a second example for repeated eigenvalue for 2 by 2 homogeneous system. Where first step we find the eigenvalue by letting the determinant of A minus lambda I equal to 0. In this case, we find two same eigenvalue. Then step 2 finds the V1 from A minus lambda I V1 equal to 0. And then here we got two versions. One is letting y equal to negative s. Another version is letting y equal to s. So different assumption, we have different general solution, like different general solution. But when we plug in the initial condition, we have the same particular solution. Because here for this assumption y equal to negative s of v1 is 3 negative 1. For y equal to s of v1 is negative 3 and 1. And then finds a v2 from a minus lambda I v2 equal to v1. Okay, so the red color is a version y equal to s. So for y equal to negative s, your v2 is 1, 0, but for the version y equal to s, your v2 is negative 1 and 0. Okay, this your v1 also different signs. Yeah? It's 3 negative 1, this negative 3 and 1. And then we plug in to the general solutions. A v1 exponent lambda t plus b v1 t exponent lambda t plus b2 exponent lambda t. Okay, and then for two variations, after you plug in the initial condition, here a b different, a and b different signs. But after we plug in the particle a and b expand, you will get the same solutions. With this, thank you for your attention.